All right, to wrap up section, what are we in? 7.1. So to wrap up section 7.1, we're going to look at functions as equations. So this video might be a little bit longer. We have one, two, well, maybe not. We have three examples to look at. Okay. So what I would say about thinking of equations as functions is don't overthink it. Okay. It's kind of like secret code. Okay. We have an equation. We, the mathematicians, know it qualifies to be a function, so we just put this special notation on it that says, hey, it's a function, okay? So just kind of like really quickly to let you understand like what we're about to do, let's say we have y equals 2x plus 1, okay? This is just a regular old equation. It happens to be the equation of a line, which we'll learn more about in the next section, but we just have this regular old equation. I am here to tell you this regular old equation does fit the bill to be a function, okay? So if we were to write this as a function, all we would do is change how we write the y, okay? Saying y equals 2x plus 1 is absolutely okay. But to indicate to your reader, like, hey, this is also a function, we would just replace the y with f of x, okay? And this does read f of x, okay? It doesn't read f times x, it's f of x. So think of f as function and x as the independent variable. So think of this as, instead of saying f of x, we could say, this is the function in terms of x, but that's kind of mouthy, or mouthy. So we just say f of x, the function in terms of x, okay? So all you do is replace y with f of x. So let me erase the highlighter spot that I just made. So instead of saying y equals 2x plus 1, we would say f of x equals 2x plus 1. We're just indicating that, hey, we know it's a function. That is the only difference, okay? These two equations are exactly the same thing. One, we're just telling the reader it's a function, whereas the other one isn't, okay? It is a function, we're just not saying it's a function, okay? Now, ordered pairs can be a little tricky when you see them typed out. This right here is the same thing as x, y. Just remember, we replaced y with f of x. So when you see people talk about functions, they'll sometimes represent the ordered pairs as x, comma, f of x. Remember, f of x is just y, okay? So x would be considered your input value, and then f of x is considered the output value. Remember, this is really just y. Okay. And you might be like, well, if it's all the same thing, why the heck do we do it? We just do. This is how we indicate to our reader. This is how we in math use functions. Okay. So this is referred to as function notation. So when you replace your y with f of x, you're using function notation. Okay. So what's cool about function notation is it allows us to evaluate functions pretty easily. It's just kind of like a nice shorthand. So let's go back to that idea, y equals 2x plus 1. I could ask you to find y when x is 0. Okay, so you would say, okay, y equals 2 times x, but x is 0 plus 1. So y equals 0 plus 1 equals 1. So we would get the ordered pair 0, 1. Okay, no big deal. We've done this in previous videos. Okay, remember, we were finding tables of values. It was basically doing this. Well, now when we're in this world of functions, if we have f of x equals 2x plus 1, I can ask you to find y when x is 0, but all I would ask you to do is find f of 0. Okay, this is the same thing as saying find y when x is 0. This is your input, which is really the x value, and then whatever we get becomes our output. So we would say, well, f of 0 equals 2 times 0 plus 1. So f of 0 would equal, well, 2 times 0 is 0, plus 1 is 1. So f of 0 equals 1, which corresponds to the ordered pair. Whatever's inside parentheses is your input. Whatever you get on the other side of the equals is your output. This would correspond to the ordered pair 0, 1. Okay, so it's just a different way of representing a regular old equation. It's just this type of equation happens to meet the criteria to be a function, meaning each input corresponds to only one output. Okay, so let's go ahead and practice this function notation. Okay, so we are told here, for example, this is not example 4. I have got serious typos because we should be on like example 10. I'm really, really sorry. So this should be example 10. This is what happens when I copy and paste and watch TV while I'm doing it. That should be example 10. This should be example 11. And this should be example 12. I am so sorry. And that's probably not the first time that's happened because I do copy and paste a lot. All right. So for what should be example 10, it says if f of x equals negative 3x plus 4, find each of the following. So this right here is the function that we're looking at. All right. And we want to evaluate that function for three different values. First, negative 5. Part B, we're going to evaluate it for 0. And then part C, we're going to evaluate it for 7. Okay. So I would say f of negative 5 equals, well, I'm going to rewrite that function, but anywhere I see an x, I'm going to replace it with whatever is inside parentheses with that f of stuff. Okay. So I would get negative 3 times x, but we're going to say x is negative 5 plus 4. Well, I would then just follow the order of operations. Negative 3 times negative 5 is 15. And then 15 plus 4 is 19. So I would say f of negative 5 is 19. And as long as you're dealing with strictly numbers like this, we could say that this corresponds to the ordered pair. Well, whatever is inside parentheses is your x, and then whatever you get on the other side of the equals is your y. So that corresponds to the ordered pair negative 5, 19. Okay? Now, next up, we're going to take the same function, but we're going to evaluate it for a different value. We're going to evaluate it for when x is 0. Okay, so remember, this is just when x is 0. This is when x is negative 5. So f of 0 equals negative 3x, but x is 0, plus 4. So f of 0 equals, well, negative 3 times 0 is 0, and then 0 plus 4 is 4. So f of 0 equals 4. And then this corresponds to the ordered pair 0, 4. It's that simple. It's just a way to represent that we understand and acknowledge that this is a function. All right. Finally, f of 7. So we're going to evaluate the same function when x is 7. So we get f of 7 equals negative 3x, but x is now 7, plus 4. So f of 7 equals, well, following the order of operations, we want to take care of negative 3 times 7, which would be negative 21, plus 4. And then let's see, negative 21 plus 4 would be what? Negative 17? All right, and that would correspond to the ordered pair 7, comma, negative 17. Just remember what is inside parentheses is your x, and then what you get on the other side of the equals is your y. Okay, now let's practice that again with just a different function. So this time we have for what should be example 11, if f of x equals x squared plus 3x minus 5, find each of the following. So we want to find f of negative 2. So this is telling us x is negative 2. So f of negative 2 equals, rewrite your function. Anywhere you see an x, replace it with a negative 2 using parentheses. So x squared is going to be negative 2 squared plus 3 times x, which is negative 2, minus 5. Following the order of operations, we're going to do exponents and multiplication. So negative 2 squared is 4. 3 times negative 2 is negative 6, and I'm just going to write that as minus 6, and then drop down your minus 5. And then f of negative 2 equals 4 minus 6 is negative 2. Negative 2 minus 5 is negative 7. And this would correspond to the ordered pair negative 2, negative 7. All right. Two more. F of 0. So if we have f of 0, that means x is really 0. So we would get f of 0 equals, we're going to rewrite the function. Anywhere you see an x, you're going to replace it with a 0. So we get 0 squared plus 3 times 0 minus 5. Well, 0 squared is 0. 3 times 0 is 0. And then drop down your minus 5. And finally, 0 plus 0 minus 5 is negative 5. Let me get a sip of water. All righty, and this would correspond to the ordered pair 0, negative 5. Okay, one more. All right, so we have f of 3, which means x equals 3. So we're going to rewrite the same function, but anywhere we see an x, we're going to replace it with a 3. So we get 3 squared plus 3 times 3 minus 5. Well, 3 squared is 9. 3 times 3 is 9, so I'm going to go plus 9, and then drop down your minus 5, or minus 5. And then let's see, 9 plus 9 is 18. And then 18 minus 5 is 13. And this would correspond, if I were to write this as an ordered pair, this would correspond to the x value is what's inside parentheses, so the 3, and whatever you get on the other side of the equals is your y. So you can see we input a 3, and it'll spit out a 13. Okay, so that's kind of how you can think of the input-output. Okay, now one more big topic that we have to cover. It's still part of the same topic 6, but it's just kind of like a new part of it. We have something called the vertical line test. The vertical line test is used to determine if a graph is a function or not. And it's really, really easy to tell. Okay. Now I'm going to have to give you some information that you have to just kind of take me on faith. You'll learn about vertical lines in the next section, in section 7.2. But please understand that all lines are functions except vertical lines. Okay, so do I have room down here? I don't. Okay, so imagine, if you will, a vertical line like such. Okay, so we have this point right here, which would be the point 3, 0. We could have a point up here, which would be, let's say, 3, 2. We could have a point down here, which would be 3, -3. Okay, so I know that's really hard to see because it's super scrunched, but hopefully what you notice about those 3 ordered pairs on that vertical line is that they have the same x's. And if we go back to the definition of what is a function, okay, so we scroll all the way back to what is a function, we have this right here. Okay, a function is a special type of relation where each input value, so each element in the domain, can correspond to only one member of the range. Okay, so that means x's cannot repeat. But if we go down here and look at this idea of a vertical line, well, golly, our x's repeat. So all lines are function except vertical lines because all solutions to a vertical line have the same x, meaning x's repeat. So what we know about lines so far, they're all functions except a vertical line. And we use that to our advantage because we know a vertical line is never going to be a function. It has repeated x's, okay? So this is how the vertical line test works. The vertical line test says if any vertical line intersects a graph in more than one point, the graph does not define y as a function of x. Meaning, if a vertical line intersects a graph at most one time, then you have a function. So if an imaginary vertical line intersected your graph more than once, not a function. If it intersects your graph at most once, then you have a function. So you just kind of sweep a vertical line across your graph, and if at any point you would intersect the graph twice, you know you don't have a function, or more than twice, okay? So right here, for example 12, it says determine if each graph is a function, okay? So if you can look at part A is kind of wacky looking, but could you sweep a vertical line across this graph and ever touch the graph more than once? And the answer would be, well, no. I'm going to use red so you can see it clearly. If we have this vertical line right here, we would eventually cross the graph like down here just once. This vertical line crosses the graph only once, only once, only once, only once, only once. At no point would a vertical line ever cross this graph more than once. So we would say that this is a function. Okay? This one passes the vertical line test. I will generally use VLT to represent vertical line. Okay, same thing for part B. Imagine you've got like the side of a sheet of paper or a ruler that's in a vertical position, and you just sort of sweep it across your graph. If it touches the graph more than once at any point, you're not dealing with a function. So here we intersect once, 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 once. No matter where we try, a vertical line is only going to cross this graph one time. So we would say this is a function. And again, I could say it passes the vertical line test. And then that leads us to graph C. So graph C, you don't have to show every time this happens, just show that it happens once. And then you know you don't have a function. If I look at this vertical line right here, I have this point here and this point here. And these 2 points have the same x, which means we have repetition of x's, okay? So for this one, I would say not a function. And I would say this one fails the vertical line test. So the vertical line test is just a really quick way to glance. I say glance. I mean, you sometimes have to like look at your function, but it's a really quick way to glance at your function and determine yes or no, it is or is not a function. Okay. So we know what a function is by definition. We know what a function is when we look at like those little bubbles or a set of ordered pairs. We know how to indicate to a reader that we have an equation that is a function. We know how to evaluate functions for given values, and we know how to look at a graph and determine if it is a function. Okay, so that wraps up section 7.1. In 7.2, we're going to look at very specific functions called linear functions. So we're going to look at lines. Okay, and remember, all lines are functions except vertical ones. Okay, so we'll dive into section 7.2 next time.